Okay, welcome. We are looking at properties of a magnet, and we are saying that iron filings are attracted by a magnet, and also we look at the strength of a magnet is always at the end. Okay, so when we look at this visual, you'll find that when you bring a magnet near iron filings, they are attracted mostly at the ends, so they normally cling at the ends, and that shows that the strength of a magnet is at the poles. Okay, another property here, we look at the magnet attracts magnetic materials only when we move our magnet in a mixture of magnetic material and non-magnetic material. You find that it only attracts magnetic materials, okay, like that, and it leaves out the non-magnetic materials. Okay, that is also another property of another property is that when we freely suspend our magnet, okay, when we freely suspend our magnet, okay, it will rest in north-south direction, with the south pole south pole resting in the northern hemisphere and the north pole resting in the southern hemisphere. Another one is that like poles of magnets repel one another. If you have north, they repel one another, and if you have south, they repel still one another. Okay, so if you bring, well, unlike poles attract, when you bring unlike poles, they attract each other. When you bring like poles, north, they repel each other. Like poles attract each other, and unlike poles repel each other. We say like poles attract each other, while unlike poles repel each other. Another property is that if a magnet is broken into smaller pieces, the individual pieces of a magnet also become a magnet. This is according to the domain theory of magnetism, that if we break this magnet into smaller pieces, those smaller pieces are also magnets. They will attract other magnetic materials, just that the strength of the magnet will become weakened. Here, another property is that they are field lines. They are lines of force around the magnet, and they run from north end to the south end. When you use a plotting compass, you find that its north end always will point away from the north of the magnet, and you find that it will create a magnetic field or lines of force around a magnet, as we see here. Okay, so that shows that these lines of force always are traced from the north and they end to the south, like that. This visual shows that if you have iron filings around a magnet, they will cling in form of the lines of force, the magnetic lines of force. So you find that they form spherical spheres around the magnet, but still more iron filings will be at the ends than the middle. Is that magnets induce magnetism to magnetic materials. This is shown when we get our magnet and we suspend it freely. Then you bring iron filings near. You find that if one iron filing is magnetized, it will also magnetize another one and magnetize another one, like that. So this one shows that there is induced magnetism in the iron filings that are following one another. Induction is whereby something tends to behave as if it is the one inducing it. Like here, these iron filings tend to behave as if they are magnets, but in actual sense, if you remove that magnet, you find that these iron layers will fall. So they induce opposite polarity at the near end and similar polarity at the far end, south pole of the Earth's magnet. And in the geographic south, we have the north pole of the Earth's magnet. So you find that in the Earth itself, there is you see, we have the magnetic south pole here, and we have the magnetic north pole. In the northern hemisphere, this is our northern hemisphere, we have this we have the south pole of the Earth's big magnet. The Earth behaves as if it has a permanent big magnet. So it is in its north pole is in the southern hemisphere. This is called the geographic south, and this is called the geographic north. So this is where the south pole of the permanent Earth's magnet is located, and this is where the north pole of the Earth's permanent magnet is located. That is why when we suspend our magnet freely, so it rests in a north-south direction. For a freely suspended magnet, it will rest in a north-south direction. With if it is a freely suspended magnet, this north end will be where the Earth's south is. That is, its north end of a freely suspended magnet will be up, and its south end of the freely suspended magnet will be down, because down, that is where the geographic north is, and up, that's where the geographic south is. Right. If you look at this vision, it clearly shows that this the south end of our Earth's magnetism is located up in the northern hemisphere. You understand? Then the north end of the Earth's magnetism, I said it has a big stone that is magnetic in nature, is in the southern hemisphere. Okay, so the yellow line represents the magnetic axis, and the white line represents the geographic axis, which is the axis of rotation of the Earth. Okay, so we are saying that when I suspend now my normal magnet on Earth, it will not rest horizontally, but it will follow this direction, north-south direction, whereby the north end of our Earth's magnet, the one I suspend, will be up, and its south end will be down, because of the attraction of opposite polarities. Okay, now here we look at the way the Earth is located. We have this vertical axis, okay, the axis of the axis of rotation of the Earth. Now we have, if you look at the green, we are calling it the magnetic meridian. The magnetic meridian, and the red, I beg your pardon, the green is supposed to be the geographic meridian, and the red is supposed to be the magnetic meridian. It is a vertical axis. The magnetic meridian is a vertical axis which contains the axis of a freely suspended magnet. Then the geographic meridian will be the vertical plane, is the plane which contains the axis of rotation of the Earth. The axis of rotation of the Earth. Now, when you look at this visual here, our north pole of Earth's magnet is here. Field runs from the north and end to the south, like that. But because they run long distances, for us when we are drawing them, we shall draw them parallel, running from bottom to top, bottom to top, like that. We are going to look at how do we magnetize a magnet. What we do, we put a metal bar flat on the surface. Then we pick our magnet and start stroking. This is called a single stroke method. You pull it over. In so doing, you are making your atomic magnet align in one direction. Okay, align in one direction. So you pull it over, and thereby you make it align in a particular direction, as we're going to see here. Okay, so here your atomic magnets are being made to align in a particular direction, and therefore your iron bar now is magnetized. Here, the end, this end here, will have opposite polarity to that of a stroking magnet. The end will have opposite polarity that of the stroking magnet. Okay, and then this is the rear end, and this first end here, where we start from, will have similar polarity to that of a stroking magnet. If I change it and I used south to stroke, this end will be north. Okay, then we look at another method. We call it double touch. Still, you stroke the iron bar with the two, or steel bar with the two magnets, like that. What happens here is that this iron bar is struck in a way that we pull the atomic magnets on either end. Still, you find that the end, this end here becomes south, and this end here becomes north, because I'm stroking using my south end here, and I'm stroking using my north end. This is called double touch method. If I use the south or north, what happens? I'll get what we call consequent poles. What are consequent poles? Here you see that two magnets are used to stroke your iron bar, but I'm using similar polarities in the middle. So you find that what will be formed at the end, like I said, what is formed at the rear end should be over opposite polarity. So we have north pole here and north pole here, and 2 poles in the middle similar. So we call this one consequent poles. For a magnet with consequent poles, it will not rest in a particular direction. It will always rotate around because it has similar polarities at the ends. So we shall always have repulsion, 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 attraction, repulsion, attraction. So it will continue rotating. We can also look at this, magnetize the magnet using electrical method. Now this one shows that when current flows from this positive end to negative end, we create a field around it, and this field created has similar properties as that of a magnet. You can see closely that a field is created around. Use the right hand grip rule, whereby our current is flowing downwards. This thumb points in the direction of current, then these fingers will turn in the direction of the field. That's why you see that the fields are in clockwise direction and the current is moving down. You use your right hand to grip the conductor such that the thumb points down, then the fingers will turn in the direction of the field. Using the knowledge above, we have this unmagnetized material. You see, the atomic magnets initially are in random direction, but when current flows, they are going to be aligned in the same direction. You see, the end where we have south pole, current is flowing in clockwise direction, and in the end where we have the north pole, current is flowing in anti-clockwise direction. What happens is that initially when you have your atomic magnet randomly facing, the atomic magnets in the magnetic material are not magnetized. Current aligns them in one direction, and when they are aligned in one direction, then they form a magnet. This is the electrical way of forming a magnet. Okay, so the easiest way to try it out, when you grip your conductor, okay, and now if current is flowing in a clockwise direction, when I grip my conductor and the current is flowing in a clockwise direction, then that end where current is flowing in clockwise direction, that end becomes south pole, and then the other end where current is flowing in anti-clockwise direction, that end becomes a north pole. Or you can try to use your right hand to grip this solenoid. These fingers are pointing downwards. Similarly, our current is flowing downwards, the way you see it, okay? So it is flowing in downwards, and if it is flowing downwards, this thumb is pointing in the north end. The thumb will point in the north end. If we turn it like this and the fingers current was flowing upwards, then the thumb will point this end, and therefore that one will be the north end. So here, as the way the current is flowing, it is the thumb is pointing in the north direction and the fingers are pointing in the direction of current. Remember, we have said when current flows, it creates a magnetic field around it in a conductor or a coil. Now, when you look at this arrangement, this is what we call an electromagnet when it is magnetized. So we have a coil wound on a magnetic material. When we switch on, make sure you switch on like that, current flows, and in so doing it will magnetize. You can use the same principle where current flows in anti-clockwise direction, that end becomes the north pole, and where it is flowing in clockwise direction, it becomes the south pole, and you find that it is going to attract the ion filings. If I switch off, it ceases to be a magnet because this is a soft iron core. When you switch on, it becomes a magnet. Switch off, it ceases. So it means that magnetism is as a result of presence of what? Of current. When current is not there, then this one is no longer a magnet for a soft iron core. However, if I use a steel, a hard magnetic material like steel, you'll find that for it, yes, to take time to be magnetized, but when it is magnetized by current or any other thing, its magnetism does not go easily. Even if you switch off, current stops, but it remains with its what? Magnetism. Okay, so that is for a hard magnetic material. But what I want you to understand here is that current flowing creates a magnetic field, and that field has exactly the same property as that of a magnet. Okay, now we are going to look at how to demagnetize a magnet. We can demagnetize the magnet by heating it or hammering it. So when you hit it, the already aligned atomic magnets will be disorganized, and they will face in a random direction, meaning that you have demagnetized this, you have demagnetized it completely. So they are in one direction, now they are in random direction. So that is how you demagnetize, and you rest it in east-west direction, such that there are no chances of organizing them again. If they are north-south direction, then the Earth's magnetism will organize it in order, such that again it becomes a magnet. But because it is in east-west direction, it will never be magnetized again. You can also heat, boil, heating with HEAT. So when you heat it, it stops to be a magnet. You are disorganizing the arrangement of atomic magnets. You can also put it in alternating current. This alternating current, what happens? It disorganizes the way, because it is this direction, the other direction, this direction, the other direction. So in so doing, you are disorganizing the way the atomic magnets are arranged. Okay, when you do that, you are disorganizing the way the atomic magnets are arranged. Therefore, it will stop to be a magnet. Look at what we call a magnetic field. A magnetic field is a region around a magnet where a magnetic force is experienced. So when you look at these iron nails, the three of them, at a distance, equal distance from each other, when we bring a magnet near the first one, you find that it will be attracted. Then the second one will experience a slight force, and the third one will not, meaning that in the third part there is no force experienced. Okay, so it is attracted, then the second one is about to be attracted. So it means that in near nail 2, that is where the magnetic field ends, and it is stronger near the magnet and weak at the extreme end. We can try to trace the region using a plotting compass. That plotting compass always run from north and ends to the south end. Always run from the north and ends to the south end, like that. So that sphere is what we call a magnetic field line. Okay, so lines around a magnet that indicates the region where the force is experienced, we call the magnetic field. We are going to look at how we can trace the magnetic field in the lab. Place the magnet on a flat surface, put a plotting compass at the extreme from one end to another. So you will find that it creates a region around a magnet, and that region behaves like that. Okay, in that the north end of a compass, is repelled away from the north, and the south end attracts the north until it is complete, like that. So then you do the same downwards until you form your region. So this region around this magnet is what we call a magnetic field. So magnetic field lines between opposite poles will look like that. You have the south pole and the north pole. They always run from the north and end to the south. Here we are trying to show you how the fields run from north and end to the south. When you have two opposite poles, the north, two similar poles, the north and the north, they will create a point X. This point X is what we call the neutral point. So they repel one another. When you look at these fields critically, they never cross one another. They are of the same distance from each other. So that is how the fields behave. Okay, lines of force in the same direction always repel one another, but there's a point whereby the resultant force is zero. Okay, you have opposite polarity. So here you are trying to draw everything. So we have lines of force running from north to south, but there are other lines of force running from this north to south, north to south. Okay, like that. So this is it when you have drawn everything, what will be shown ideally. So when you have two magnets on top of each other, this is how the fields will behave. Lines of force will run from north to the south, north to south. Others will run away, others would go downwards and will be attracted here. Then these others which run away, these ones here, will come and enter the south end here, like that. Then the others which will come still here and enter the south. So others will come and enter the south end, like that. So that is how it behaves when you have one on top of the other. Okay, so here still you have south. Okay, if south, then these ones will run from north, enter the south, then those ones run from the north. But remember, when they are in the same direction, they repel one another. Okay, we can't have these ones coming this way, but they will go to the south like that. Okay, that is when you have them south south. The other one, we had them north south. They are different. Okay, so you can look at both and try to. So when they are opposite polarity, they can link between two magnets. You can see they link between two magnets. When they are similar polarities, they can't link between the two magnets. These two magnets behave as if they are independent, but because of repulsion between the fields. Okay, now when you look at this, when you have your magnet and you place it vertically in the Earth's magnetic field, so we shall have these fields here. This is Earth's magnetic field. Remember, it comes from north. Now it finds this a permanent magnet suspended vertically like that. You will see that fields from the Earth will enter the south because they are coming from north. Others will come and bend to the south. Others will not even bend, they will just continue moving up. But there is a bend here. This is a point where the attractive force is no longer there. It's a zero. So it can attract up to a particular point. At this point, we have no resultant force. You find that when this thing here is this one here, the compass is placed here, it will just rotate around. It will never settle like here. It rotates. There is no force there. Resultant force is what? Is a zero. As simple as that. So you find that these fields, for them, they run up like that. So these ones tend to be probably attracted down, but they can't reach because again they will be repelled here. So that is how it looks like. Okay, so when you have the north end pointing downwards like this, the shape differs from the other one. Remember now, this north is going to be repelled by the other north of the Earth. So the fields that run from north will not enter here, but they will come and enter up here on the south, north, south. Okay, even the fields from the magnet itself will enter the south like that. So at this point X, we said at that point, point X, we do not have magnetism, magnetic force. The resultant force is zero at that point. Okay. Domain theory of magnetism. Now when you look at this, this is how a magnetic material behaves. It has atomic magnets that are aligned in opposite direction. So this region is a domain. This is a domain. This is a domain. This is a domain. This is a different domain. It's a different domain like that. So you find that in a particular domain, all the atomic magnets are in one direction. They are in one direction. In another domain, they are in another direction. So we find that in a magnetic material, the atomic magnets are arranged in various directions. Now, if you want to make it a magnet, so you make sure you use a magnet to align all the atomic magnet in one direction. So you align all the atomic magnet in one direction. Align all the atomic magnet in one direction. Therefore, you are magnetizing. The other methods we saw of magnetizing a magnet, this is what we do when you want to magnetize. You can use electrical method, you can use stroking method. So you are, in actual sense, you are making the atomic magnets be aligned in one direction. Okay, so domain suggests that the atomic magnet, the magnetic material is made up of small atoms. Those small atoms are magnetic in nature. In unmagnetized state, the atomic magnets facing in random direction. When you magnetize it, they will be aligned in the same direction. Now, when you break this magnet into small parts, even up to the smallest part of an atomic magnet, it will still behave as a magnet, and that is what we call domain theory. Now, when you look at a magnet that is magnetized, okay, what happens inside it? It has atomic magnets that are aligned. Okay, these atomic magnets, those atomic magnets here are in random vibrations about their main position. Okay, now what happens is that when you they're in opposition, when you magnetize them, they will be forced to align in the same direction, with the south end, north end, south end, north end, south end, north end, like that. Now, you see, when you start magnetizing, okay, like that, you find that this smallest part is the one which is magnetized. Okay, now when you continue magnetizing, you increase the number of atoms that are in the same direction. When you completely magnetize like that, then you know that all of them are in the same direction. So we call this one magnetic circulation. Magnetic circulation is whereby all the atomic magnets in a particular magnet are made to align in one direction. Okay, we are going to talk about magnetic shielding. If you look at this magnet, fields are running from north and they end to the south. Okay, shielding means that you prevent these magnets to reach the south. What you you prevent them to reach the south. In case we place here what we call a magnetic material, a ferromagnetic material around here. When we put it here, it will just concentrate the fields to itself like that. You see, it is trying to prevent them. So in this region where we have placed our magnetic material, there are no fields that will run through that point, so we can keep our magnetic material that we don't want to be affected by magnetism. So in this region here, there is no force of magnetism here. Example, when you look at your watch, it has that circular path. That circular path, its work is to concentrate all the fields such that the hands in the middle are not affected by the magnetic fields. So that is shielding. Okay. We can also talk about shielding here, whereby you have these iron filings or clips that are going to be attracted by this magnet on top here. It is attracted when we put a pencil. Okay, oh, of course pencil is helping us to support the two boards. When I put a knife, the clips fall, meaning that the magnetism is now concentrated in the what? In the knife. Okay, concentrated in the knife, and now the clip will no longer receive the what? Will no longer receive the force. Okay, that other thing is another unmagnetized material, which actually non-magnetic material. That one is a magnetic material, so it concentrates all the magnetism such that I shield the magnetism from reaching the clips. Okay, how do we store our magnet? We use keepers to store our magnet. Now, what we do, we place a board, place a magnet in that format. Make sure the north is next to the south. Okay, then bring that keeper, that is a piece of magnetic material, put it on top. Then you get another one, put it at the bottom. Then you find that there is magnetic circulation. Actually, what happens is that this one induces the north here, and this one induces the south here. So this one temporarily behaves as a magnet. So we shall have a circulation of magnetism, meaning that we shall not lose any magnetic field around. Therefore, we have kept our magnet safe. We call that one a magnetic keeper.